Okay, I wanted to make a video for you all about a couple of the problems from this second part 2 of chapter 2, and I wanted to talk about 61 and 63 just to show you a couple of tips on how to get these things done. So let's just read this one. A steel ball is dropped from a building's roof, passes a window, taking 0.125 seconds to fall from the top to the bottom, and it gives you the distance. And then it falls to a sidewalk, bounces up past the window again, moving from bottom to top in the same amount of time, 0.125 seconds. Assume the upward flight is exact reverse of the fall. The time the ball spends below the bottom of the window is 2 seconds. How tall is the building? Well, so that seems like a tricky problem. And there's one thing to do in here that's kind of necessary to figure this one out. So I always, like to draw a picture. So there's the window, and here's the ball. Gets dropped from some height up there, and it falls down, and then the time it takes to go past the window, that total time was 0.125 seconds, and then the distance right there, which maybe we can call the height of the window, is, where was it? 1.2 meters. Great, so that's what we got. And then it's going to come down here, it's going to bounce, it's going to do the reverse with these same times and heights right here. And the question's really asking how tall is the building. So it's asking how high was this drop all the way down to there. So if we're thinking about, I'm going to switch to pencil in case I need to erase. If we're thinking about how we would figure out how high something is, we have a couple ways we can do it. Most likely is going to be our good old 1/2 ET squared equation. Right? And then all we really need to know is how much total time it takes to fall all the way down, this whole thing right here. Well, we know how much time it takes to go from here to there. Oh, by the way, this whole time for this bounce and come back is 2 seconds for it to bounce and come back. So we know it's 1 second from there to there and then 1 second back. So we know this time is 1 second. We know the time from there to there is 0.125 seconds. So if we could somehow figure out the time from there to there, we could stick it into this formula and then we're good. By the way, we have no initial velocity. And if we set our x equal to 0 right here, then we have no initial position. Maybe just to keep things a little easier to work with, let's just do something slightly unconventional here, and let's make positive in the down direction. That way all of our values are going to be positive. We don't really care about the bounce, because all we really care about is just this time going down. So let's make positive down, and that way acceleration is positive, and all these velocities will be positive here. It just saves us the trouble of working with a bunch of different velocities. So the trick is, once again, if I want to figure out how much time it takes to go from there to there, and I need that because I need the total time to go all the way down, I have to kind of know what this distance is right there. So I kind of want to know what this distance is right there. And in order to know that distance, I kind of need to know, well, how could I figure this out? If I know what the velocity is right here, I could work backwards with v equals at plus v0. If I know the velocity here, then I can work backwards and figure out, well, how much time it took to fall. If I start out with 0 velocity and I know the velocity at this point, then I'll know the time it takes to get from there to there, and that would be pretty good. So somehow I've got to figure out what the velocity is right here. If I just take these two things right here, and if I just do kind of the thing you might want to do, which is to take 1.2 meters divided by 0.125 seconds, which is going to give me around 10, but let's see, 1.2 divided by 0.125. Oh, whoops, that was wrong. 1.2 divided by 0.125. There we go, 9.6. Oops, that's seconds. 9.6 meters per second. Now you might be tempted to think like, oh, well, that's what my velocity is. But really what this is this is going to be the average velocity for the time the ball takes to get all the way past the window. That's the average velocity. So how do I figure out what the velocity is here? Clearly it's going to be a little bit less here and it's going to be a little bit more right there. How do I figure out the velocity there, which is kind of strange? You might think, oh, I know, well, we'll just go v squared equals v0 squared plus 2a delta x. And that way, I know the acceleration, I know the delta x here, but this equation is weird because I need to know both velocities. I need to know the velocity here and here, or here to get this one, or here to get this one. Initial velocity, final velocity. All I really have is the average velocity. So that's a little bit tricky. So what could we possibly do to get that? Well, let's think about what average velocity is going to mean. Like if I drew a velocity graph for this entire journey right here, I'm once again going to make things going positive velocity over time, even though it's going down. So there's the ball dropped. Remember, the velocity graph is always a line. Well, it was a pretty good line. I know that the slope of this line is 9.8. And then here's my window. So from there to there is the window, or something like that. Right, so it passes the window at this time, which I don't know what it is. I know that this is 0.125 seconds from there to there. And I've got this initial velocity at the top of the window right there. Maybe we'll call that like V1, and maybe we'll call that V2. So here's my V1, and then there's my V2. Of course, it's going to bounce off the ground and things like that way over here. So how do I figure out V1 if all I have is the average? Well, good thing we're dealing with things that are linear, because the average is going to be right in the middle. So I know that this right there is 9.6 meters per second. That was terrible handwriting. Let's try that again. 9.6 meters per second. That's the value right in the middle right here. So if I know the middle value, I can find either of these values over here because I know what the slope is. Yeah? So let's work backwards to figure out what this one is. So this 0.125 seconds, half of that, 0.125 divided by 2, so that's going to be 0.0625. So that's the time from there to there, 0.0625. So if I know this run, I can figure out what this rise is based upon the slope. Right? See how that's going to work? So I'm going to let you all figure it out from there. Yeah, so once again, if you know the average velocity, you can figure out V1 and V2. I guess we could also put it like this. Average velocity is V1 plus V2 divided by 2. Does that help us? I guess we don't really know either of these. But yeah, so maybe going back to my original method, if I know this is 0.625 seconds, I can figure out what this is. And that would take me from the average velocity of 9.6 back to V1. Once I figured out what V1 is, then I can use this equation. Here's what V1 would be. No initial velocity at the top right here, so I could figure out how much time it takes to do this. Then I know the time it takes to fall to there, the time to pass the window is 0.125, and the time to hit the ground is 1 second, and I could plug it all back into this to find my total distance right there. So that's just one way to do the problem. I didn't solve it all the way because I'm going to let you all figure some parts of it out. There are other methods too, but I think that that's a clever method. And it'll also work for number 63 here. So if we look at 63, drowsy cat spots a flower pot that sails first up and then down past an open window. The pot is in view for a total of half a second. The top to bottom height of the window is 2 meters. How high above the windows does the flower pot go? Same thing, draw a picture so we know what's happening here. There's the window. We know that the flower pot is going to go up past the window, whee, and then down like that. It would be really great. We're trying to find this height right here. If we knew what the velocity was right there at that point, if we could figure out what that velocity is there, then we could use our good old v squared equation. V0 squared plus 2a delta x. We could say this velocity and putting it in there, and then the velocity at the top is 0. We could put that in there. And then our acceleration we know is negative 9.8, put that in there, and then we can figure out what the distance is right there, right? This time I would suggest keeping plus up and negative down. I think that that's going to make it a little bit better for this problem. So how do we find the velocity right there? Well, we do know that the top to bottom height of the window is 2 meters. So my height of my window is 2 meters. And then the pot is in view for a total of 0.5 seconds. So that's the up and down. So for just the up part, I could say that that's a quarter of a second, 0.25 seconds. From here, I could figure out my average velocity passing the window, which would be 2 meters over a quarter of a second. So that's going to give me 8 meters per second. That's my average velocity. And then from there, I could figure out what the velocity was here, which is going to be a little bit less. So this is the velocity in the middle of the window. It's going to be a little bit less going right there. And once again, it's a linear relationship. This time the graph might look like this instead. And I have my average velocity from here to there, right? From there to there. But basically the same method as what we did up here for this one. So that's some just little ideas on how to solve that problem. The other ones I wanted to talk to, it still takes some work, right? I'm not solving it for you, so I'm still making you do some work. The other ones I wanted to talk to you about were some of these ones where we have to deal with area, because we didn't talk about this in class so much. So let's look at number 69 right here. And you don't have access to the online book is the other thing, so that's making it tricky for you to go look things up in the book. So right here, it says, how far does the runner whose velocity time graph shown in figure 240 travel in 16 seconds? VS is 8. So this is 8 right there. So the idea here is that if you find the area of a velocity graph, that will tell you the displacement. So if I just find the area of this velocity graph, it'll tell you the displacement. So it's kind of a pain because I've got this triangle here, I've got this rectangle there, I've got this triangle here, and I've got kind of this rectangle left over. So finding out all those areas, and then we can figure out what the displacement is going to be. We know he's starting from rest, and we'll assume that he starts with x0 equals 0. Remember, displacement is delta x. That's final position minus initial position. We can kind of assume the initial position is 0 and figure out what his final position was, or that's really his displacement is how far he went. So just finding the area, that is fine. Not too hard to do. And then the other one to deal with area, this one is an area problem up here with the helmet and the not helmet and the bike wreck. I think it's a bike wreck. And then the other one is this problem over here, which is now we have an acceleration graph. So acceleration here is this point right there says the set by AS equals 12 meters per second. So that's 12 meters per second squared right there. That's this dot right there. And we know the initial velocity of the particle way back here, and we're trying to find its final velocity. So the trick here is the area of this graph is going to give you the change in velocity. Which is going to give you V2 minus V1 if you want to, or V minus VO, or whichever way you want to say it. So if you find the area here, and in this particular problem, it's going to be all this area right there, which isn't too hard to do. It's a triangle. You can figure that out. This is still positive area here. It's only negative area when we go below this axis over here. And now you know the initial velocity, and you can figure out what the final velocity is. So I don't think that, oh, sorry, you actually have to go all the way down here. Oh, I didn't see that till 6 seconds. Oh, so you actually do have to go down here, add in this area, and subtract out this area from the whole thing. So this is going to be positive change in velocity, and this is going to be negative change in velocity down there. So that's just how to do a couple of the problems. There are some other tricky ones. You know, this one can be a little tricky, but it's doable. Remember, the 2-dot problems are kind of medium. 1-dot problem is easy, and then these 3-dot problems get a little bit more challenging. Okay, hopefully that's helpful for you all.